Okay, good afternoon, everyone. My name is Francesco Petruccione. I'm the interim director of NITheCS, and welcome to today's colloquium. Today, we are very fortunate to have Professor Menno van Zaanen with us. Menno is a political scientist by training. Got interested in applying computational techniques to problems that stem from the humanities. Yeah. Currently, he's a professor in digital humanities. What else? Yeah, and he's also a member of SADiLaR, the South African Center for Digital Language Resources at Northwest University, as you can see from his email address. Yeah? And I think today he will share with us some of his interests in applying, in bringing together different disciplines, computer science applied to problems related to the humanities. Yeah. So Menno, we are really very happy to have you here with us this afternoon. We can already see your slides. You're most welcome to start with your presentation. Thank you very much.
Okay, wonderful. Thank you very much for the invitation. I really appreciate it. So before I really start, I realized preparing the slides that I might have lured you here with something. I mean, it's relevant, but I'll change the topic just a little bit. Not saying that I'm not going to talk about languages and describing languages. What I really want to do is looking at languages from a sense of language learning. So there's a field called grammatical inference, and the idea of that field is that you can try to find algorithms and mathematical proofs about what kind of languages are learnable. And by doing that, what I'm trying to do, and what I'll talk about a little bit here as well, is to take a look at how people learn languages and how we can describe that, or try to describe that in a formal way, and what kind of implications that has on the description of these languages. So what I'd like to do today is first give you a short introduction in what is this grammatical inference, and we're going to have a look at different approaches. So there's two kind of main approaches in this field that are typically recognized: the formal approach, which is essentially a subfield of mathematics, and an empirical approach, which is more related to computational linguistics, digital humanities, perhaps some engineering as well. And I'll end with a few slides on actually using these grammatical inference techniques in practical problems. So really applied, and there are more open problems there, and there's a bit of a challenge there as well. Okay, so let me try and introduce this grammatical inference. Grammatical inference, the task is about learning, so machine learning or formal learning of the grammar given information about the language. Okay, so now you might actually say, whoa, wait a minute, weren't we going to look at languages and describing languages? Well, that's this grammar part, and I'll give you some examples of this. So I'm not really a mathematician, so I'm not sure if there are a lot of mathematicians here who are going to ask me difficult questions about the mathematics side. I'm more interested in kind of the boundary of the fields of grammatical inference, so reasoning about what learning can be done, but also relating that to how people learn language. So how can we describe in a formal way how people learn their language? And can we reason about these processes, and can we reason about these descriptions of these languages? So I think that's more the part of the digital humanities side. Okay, so I already highlighted, I said, and in the abstract as well, that we're going to talk about learning languages or describing languages, but now I come up with when doing something about a grammar. So there are two parts here that are a bit more difficult. You would ask yourself, why a grammar? So you could ask yourself, why a grammar and not the language that I originally promised? And why a grammar and not the grammar? So I'll quickly talk about these two. Okay, so first of all, learning a grammar versus learning a language. The idea is that if you are learning a language, so I assume all of you have learned the language because we're kind of communicating, or at least I'm talking and I hope you understand me. That then means that you've learned the language. But if you've learned the language, you need to have some sort of representation of this language. So in this case, it will be in your head. You have some sort of representation of this language in your head, so you can use that language. And this representation is called a grammar. So the task in grammatical inference is, in a way, you want to learn that language, but you do that by learning the representation of that language. So you're learning a grammar. Okay, so now there is a bit of a problem there, because when people or when machines or algorithms are learning a language, they can actually use different representations. And if you want to check whether two learners have learned the same language, you need to check whether their representations are equivalent. But this is actually an undecidable question. So from a formal perspective, it's very difficult to check whether two learners have actually learned the same language. And so I find it quite interesting on the one hand from a formal perspective, but also then we can ask ourselves, so what does it mean that we speak the same language? So is there a thing called English? So is my English, is that the same as your English? And how do we test whether our Englishes are the same? Or if we're speaking a different language, I also speak Dutch. So is my Dutch similar to other people speaking Dutch? And in a way, what you'd like to know is, what is this representation that we use for these natural languages? And we don't actually know. So there's a whole field, a whole area in the field of linguistics that looks at writing down or developing representations that can be used to describe natural languages. So there's a lot of open questions in this area. Okay, so what does such a grammar or description then look like? So I'll give you a few examples here. So let's assume you want to describe something like a formal language, right? So I've got an example there. This is an infinite language, so it contains the sentences AB or AB, AB, or AB, AB, AB. And well, I can go on, but I can go on. I mean, I think you see the pattern, right? It's AB and you can repeat it as many times as you like. So if we want to describe that language, I already gave a kind of an informal grammar, an informal description there at the top. But this requires you to understand what I mean. This is not extremely formal. It kind of assumes that you see that there's this pattern that repeats this AB, AB. So there are also other ways of representing these grammars. On the one hand, specifically for formal grammars, you have, and I'll give some more examples later, you have regular grammars or context-free grammars, for example, but there are also formalisms that are specifically designed to describe natural language properties. So there's something like a head-driven phrase structure grammar, or HPSG, or lexical functional grammar, LFG. So these kind of grammars aim to describe more linguistic properties that we know the languages or natural languages that we speak have. Anyway, I hope it's clear that to describe a particular language, we need to have a grammar. We need to have a grammar formalism. We need to agree on how to describe a particular language. Now, the interesting bit is that with a grammar formalism, if you choose a particular grammar formalism, you can describe a family of languages. So with my kind of informal description there at the top, and I'll give some more examples of regular grammars, etc. later, you can really see that I can only describe certain things. There are some things I cannot describe. So let me quickly give you some examples here. So one of the representations that we can use, and this is on the formal side, so this is not specifically for natural language, is, for example, finite state automata. And these can, so finite state automata can describe regular languages, the family of regular languages. And I'll come back to these families later. So you can define a finite state automata by a quintuple Q, sigma, Q0, F, and delta, where Q is a set of finite set of states. We have sigma, which is a finite set of input symbols. So these are kind of the letters or the words that we can recognize. Q0 is a start state. F is a finite set of final states, which comes from that set Q. And there's a transition function that takes a state, an input symbol, and maps it into another into another state. Okay, so this is the kind of general description of a finite state automata, but let me give you an example, and I'll give you 3 different ways of describing well, one specific language. So on the one hand, I'm not sure if you can see my mouse, but on the one hand, in the bottom left, there's this formal description, right? There's this quintuple with the, now we have a concrete set of states. It has 5 states. We have a vocabulary of the letters B, A, and an exclamation mark. There's a final state, and there's a transition function defined there as well. So some people can easily read this. A lot of people find this extremely difficult to see. So we can also try other representations. So this is of the same grammatical formalism, or the same grammar even, where you could look at that visual representation at the top. So this describes the same thing. Q0 is the start state, and by recognizing the letters B, A, etc., we at some point can end up in a final state Q4. And if we end up with a particular input in this final state Q4, then we say that that sequence is recognized in this language according to this grammar. So if we have this an input sequence Q, for example, just the letter Q, that's not recognized because going from our start state Q0, we cannot recognize an X. But if we have the string BAA exclamation mark, then we can just follow the arrows and end up in this final state. And we also have that loop there in state Q3, so we can actually have as many A's as we like. I hope the representation is clear, but just simply following the arrows, we can get into this final state. Another representation that some of you might have seen before is this regular expression that essentially describes the same way in a compact way. So this is typically used in programming languages, for example. So this is one representation, or actually 3 representations of the same grammar formalism, one grammar within this grammar formalism. Now, there are also other grammar formalisms. So what's often used in natural languages to describe natural language structures, natural language sentence structure, is the family of context-free grammars. They describe the family of context-free languages, and they work using these kind of rewrite rules. So in this case, I have a very small grammar that says you can have an NP, which in linguistic sense for a noun phrase. You can create an NP by selecting the first rule, for example, that says, well, you need a det, which is a determiner, followed by a nominal. And a determiner can be either the word a, or it can be the word the. A nominal can be rewritten as a noun, and a noun can, for example, be the word flight. So by kind of applying these grammar rules, we can build a tree structure on top of the words a flight, indicating that these words together represent a noun phrase. And you can also build this up for larger structures up to a full sentence, for example. So this is a different grammar formalism. It also has a different expressive power. And I'll come back to that as well. So just to quickly highlight the relationship between languages and language families, because it looks like I'm almost using them interchangeably, but they're completely different things. So assume that we have the set of all the sentences or all the sequences that exist. And I've kind of drawn that square at the right that says all sequences. So all the sequences that you can come up with are contained in that square. Now, a particular language is then a subset of that set of all the sequences, right? So there are some sentences or sequences that are part of the language and some that are not part of the language. So some will be in these ovals and some will be outside these ovals. So each of these ovals in the square on the right-hand side represents a particular language. Now, all of these languages together can be represented, or in this case, can be represented by one particular grammar formalism. So the grammar formalism defines a family of languages, right? So if we take the example of the finite state machines that I showed you earlier, all the finite state machines that can be created are contained in this language family of finite state machines, in this case, regular languages. If you do that for the context-free grammars, you get a different language family. So that describes a different set of languages, right? So a language family is a set of languages, and each language is a set of sequences. It's good to keep that in mind. So what we're doing is we're looking at properties of these grammar formalisms, and one particular grammar formalism represents one language family. Okay, so what does all of this now really mean? Well, there's this thing called the Chomsky hierarchy. So Noam Chomsky came up with this. And the idea here was really to try to describe natural languages. So what grammar formalism or what expressive power, what language family do we need to describe the family of natural languages? And Chomsky realized that there are different types of these grammar formalisms, each with their own expressive power. And he came up with this hierarchy where you see that the smallest oval, that's the smallest language family that Chomsky identifies, called the regular languages, type 3, he called that. Then there is, and that's represented using this finite state machine. So for each language in this family of regular languages, you can create a finite state machine that describes this language. There's also the family of context-free languages, and that's actually larger than the regular language. So all the regular languages are contained in the family of context-free languages. And the context-free languages are described using these context-free grammars that I showed you earlier. I showed just a small example, but all of the languages contained in the family of regular language can also be described using context-free grammars. So it's also contained in the family of context-free languages. Now, Chomsky also defined two larger families, so the context-sensitive languages that are described in a somewhat different way. They contain, so the family of context-sensitive languages fully contains the family of context-free languages, and because of that, also the family of regular languages. And then there's that final, the massive, the complete family of all languages that can be described. So that's the recursively enumerable language family. So that's fully unrestricted, and he called that type 0. Okay, so now the question is, where do we find the natural languages? Are they in the set of regular languages, context-free languages, context-sensitive languages, or in the recursively enumerable languages? Okay, so that, yeah, so you can kind of wonder why do we do this, right? So if we if we know that the family of context-free languages are more powerful, have more descriptive power, then why should we even care about these regular languages? And wait a minute, why should we actually care about context-free languages if we know that the context-sensitive languages are more powerful? Or just pick the recursively enumerable languages. We know the natural languages are in there. Well, the idea is that we as humans, we can relatively efficiently recognize language. So we also need to think about what is the efficiency of these languages. Now, I kind of showed you, so this is not a formal proof or anything, but by looking at that finite state machine, you can essentially already see, you can simply go through that finite state machine, recognizing one symbol at a time. So recognizing membership of these regular languages, so where the sentences are part of a regular language that's linear, in a linear time. For the context-free languages, this is a bit more complicated, but we can do that in cubic time. But context-sensitive is already n to the power 6, and I don't actually know the most efficient way of doing this for the recursively enumerable languages. So this has to do with efficiency. We want to have a language that is as efficient as possible, but also has enough generative power to describe all the languages. So the question is, what power do we really need? We want to essentially find that smallest family of languages that still contains our natural languages, so we can efficiently kind of recognize that. So where are the natural languages? Okay, so then we can take a look at natural languages. So really, what power do we need to describe these natural languages? And the question is, if we start with this Chomsky hierarchy, what family kind of fits best? So in which family of languages does that fit? So we know there's this trade-off between expressive power. So the larger the family, the more expressive the power, because there are more languages contained in there. But the larger that family, the less efficient it is in parsing. So perhaps perhaps the family of natural languages is not actually one of the Chomsky recognized families. It's something else, right? It might be just a whole different family of languages. But the thing is, from the Chomsky hierarchy, these families, we know what the mathematical properties are. And oh yeah, there's another thing that's actually way more fundamental. The language formalisms that I showed just now say that sentences are either grammatical, they belong to the language, or they're completely ungrammatical, they don't belong to the language. But there are some sentences, and I'll actually show you a few, where people don't fully agree. And now we're back to that question, is my English the same as your English? Some sentences where you're like, yeah, well, that could be part of the language, part of English, but I don't actually know. And some people have a stronger feeling about this than others. So we're not, with the grammar formalisms that we have now, we cannot describe that kind of vagueness. This is really a hard cut yes or no in the language. Okay, so let's take a look at some of the properties of natural languages. Okay, so natural languages contain a property called center embedding. And I've got some examples there. So a man that a woman loves, or a man that a woman that a child knows loves. And you can essentially add more there in the middle, whatever you like. So something like a man that a woman that a child that a bird saw knows loves. Okay. So this is something that can be done in English. And I fully realize that last sentence, when I hear that, I'm actually not really sure, is that really still correct? But according to the formalism, I'm not a native English speaker, so I might not have a good sense of this. But the center embeddings is something that you can do, and there are other examples of this as well. And we can show that this is not regular. So these property, or this specific property, means that for natural languages, we need to have something stronger than just the regular languages, which is unfortunate. So we need to go at least to the context-free languages. Now, in some languages, some natural languages, there's something called cross-serial dependencies. And I'm a native Dutch speaker, and Dutch is one of the languages, one of the at least two known languages where this occurs. So the other language is at least some dialects of Swiss German. So in Dutch, you can say something like, omdat ik Jan de honden zag voeren, which translates to, because I, John, the dogs, saw feed. And here you see that we don't have this kind of belonging together, but in a center embedding, but we have like a pairwise grouping, right? I belongs to the seeing, John belongs to the feeding, and the dogs also are the ones who are being fed. So we see this kind of what's called a cross-serial dependency. And we can actually show that this cannot be done using a context-free grammar. So we need to have something stronger. So we're at least in the context-sensitive language family, and that's already, parsing time is not extremely efficient. So we need to think about this. Where are the natural language? Where are the natural languages? In what family are they? So we might actually end up with new grammar formalisms that are actually cross-cutting the families in the Chomsky hierarchy. Okay, so that was enough about grammars. I also said that we need a grammar and not the grammar. So what is this about? Okay, so we had this paradox. Remember, so two learners can learn a particular language. They can use a different representation. So we can't actually check whether they've learned the same language because they're using a different representations. We can actually have multiple grammars that describe the same language. Okay, now this is very unfortunate. We want to have a way of checking whether two learners actually learn the same language. Now, so there are different ways of doing this, but they all kind of come down to defining some sort of canonical form. So we need to say, this is the standard way of describing a language. So we need to have a formalism, and even within the formalisms, there are typically multiple ways of describing the same language. So we need to kind of limit this so we get a grammar that we can actually compare. So we can, for example, ask for the grammar to be the best according to a particular score. And now what we're doing is we need to, of course, learn this grammar or learn this. We want to learn the language, but we have to choose a grammar. But we now also need to find the grammar that best describes this. So it becomes an optimization problem. We need to calculate this score that says, well, you prefer this grammar over that grammar, even though they might describe the same language. Okay, so now we need to come up with some score. So what is the best way of describing this score? And we want to have grammars that are simple. I mean, we can do this. So in our heads, we can somehow do this. So it should be, in a way, simple. It should cover the language that we are speaking or recognizing. So we should have the full coverage. So we should have a grammar formalism that can describe all of this, and it should be useful. So we need to come up with a particular score, and there's a whole range of scores that you can use. Some Occam's argument, a compression argument, Kolmogorov complexity, minimum description length. So there's a whole list of choices that you can make. Okay, now I've just tackled this a little bit from the formal perspective, but you also want to say something if you want to do some natural language learning, that you want to make sure that, I've mentioned this a few times, all the natural languages are actually contained in that class that we're learning. But you might actually want to say more. And I haven't really talked about the learning itself. So far, I've only talked about the representation. But what about the properties of the process? So how do we learn a natural language? So you might actually want to check how babies or children learn a language. What is the process that happens? What does it look like? And there are whole discussions in the field of linguistics whether children get negative feedback from the teacher, say from the parent, yes or no. And what does that negative feedback look like? So we want to describe that as well. And we might also want to say something about the quality of the learning process. So if we describe a formal learning process, does it make, for example, the same mistakes as what children make while they're learning the language? So there are a lot of additional questions that you might want to ask or things you might want to investigate. Okay, so let's take a very naive example just to kind of reason about this. Okay, so assume you're building this random number generator, and you want to check whether it works. So how can you do that? Okay, well, there are different ways of doing it. Actually, it's not so easy, but there are different approaches here. So so what about this one? You've run your random number generator, and 42 is the output. Okay, that's kind of testing it from an engineering perspective. But what does it really say? Well, by itself, it doesn't actually say too much. I mean, it's nice that it gives 42, so that's kind of random, but we don't really know if it's random. You can also say, well, I mean, I build it according to the principles defined by kind of number theory experts. So that's like this formal approach. But you can also take an empirical approach where you kind of generate not just one number, but a whole range of numbers, and you can somehow prove that the produced numbers are incompressible, right? So then you also have a random number generator. So that's the empirical approach. So there are different approaches to doing this, and these similar approaches can be done for grammatical inference as well, so for learning these languages as well. So one approach is a formal approach, where we want to show that a learning algorithm, because we're now trying to learn these languages by finding a grammar that represents this language, we can show that the algorithm has actually converged. So that means that in the limit, it reached a particular value. right? So then we've learned this language. So clearly we can't do this with just one run. That's the experimental approach, because we can't. So I've got 23 here, but 23 is just as random as that 42 that we got as our output the first time. But we can actually say something about the algorithms, right? So something like, in the near future, given some particular string, so sequence or sentence, we can predict whether this string belongs to the language or not. So that's the formal approach. So we're looking at convergence. Okay, so now we need to think about, what does it mean, the near future? And we were talking about time, future time. So what kind of time are we talking about? So we need to define all of this. And here, there again, choices. Are we talking about computer processing time, or the number of operations an algorithm can perform, or perhaps the number of example sequences that we're getting that we can learn from, or the number of changes we can make in the grammar, grammar representation that we have. And what does near mean? So when is near? And of course, here we can use something like complexity theory to kind of measure and limit the so we can look at the total or update runtime, or the size of the data needed, or the number of mind changes, or the number of times you change your specific grammar that you think describes this language, or perhaps some number and weights of the errors that you can make. So there's a lot of different possibilities here, and these are essentially describing properties of the learning process. So how does this learning really take place? Right? Are we identifying exactly a particular grammar that describes the language perfectly? Or do we say, well, with a certain small mistake, or with a certain probability, we can find the right grammar? So depending on the choices, and I've given a lot of different choices, but depending on the choices, you get different kind of learning paradigms. There's a famous one, which is a non-probabilistic setting, essentially the first that was developed in this context, called identification in the limit. So in the limit, we want to perfectly identify a grammar that describes the language we're learning. There's also an active learning setting where you can actually query the learner. So what about this sentence? Is this in the language, yes or no? But there are also probabilistic settings where you can have, with a certain probability, you get an approximation of the grammar that you're trying to find. Or you can identify with probability 1, but you might still approximate the grammar. So then it's essentially learning distributions. Okay, so let's take a look at this identification in the limit. This is essentially a very simple one. So the process works like this. You have a learner and a teacher, and the teacher is typically called an oracle. And the learner is trying to learn this language, right? So the learner has an internal grammar that the learner thinks represents the language. So we start out with a particular grammar, and the teacher gives an example sequence or example sentence. So this is a sentence that belongs to the language. So the learner can then check, so what is my current hypothesis? What is my current grammar? Does this example sentence match with that? If it matches, then everything is fine, and you go to the next example sequence. But if the learner, if the teacher, the oracle, gives an example sentence that doesn't match the current grammar, then the learner can update its grammar, its hypothesis, and then learning can continue. And the idea is that in the limit, the learner will actually find the right grammar belonging to the family. The right grammar that belongs to that specific language. So the idea is that we want to learn this not just for one language, but for all the languages in this language family, right? We're not just learning one language. We don't want to know something just about one grammar. We want to know something about this family of languages. Can we, using this learning formalism, can we learn, for example, all the natural languages? So that means that we need to show for each language in our language family that at some point, always, so for all of these languages, but at some point in time, the learner will have found the correct concept, so has found the correct grammar that describes this language, and it will not change it anymore afterwards. So if you give it more example sequences, it won't change the grammar. So that's the process of identification in the limit. Okay, so this identification limit feels like a very natural situation, right? You have if you think about natural languages, there's this baby there, you give it an example sentence because you talk to the baby. The baby is not really talking back yet because they don't really talk yet. So then we give another sentence, and we give it another sentence. And at some point, this baby or a child at that point has then learned the grammar, right? That's a very kind of simple approach. Now, unfortunately, from a mathematical perspective, you can show that you can hardly learn anything in this setting. So the NFA stands for non-deterministic finite state automata. I just showed a deterministic finite state automaton earlier. So these are not learnable in this setting. You can't learn even these deterministic finite state automata from just text, like I just mentioned. You give it a sentence, you give it another sentence, you give it another sentence. You have to keep in mind these finite state automata describe the smallest language family in the Chomsky hierarchy. And we know natural languages are not in that smallest language family. So most of these language families, even kind of relaxing the requirements a little bit, so asking for membership, for example, where the learner can ask, is this sequence part, is this sentence part of the language, yes or no? All of that is not learnable in this learning settings. There are a few positive results if you give it really additional properties, where you can check, for example, whether the grammar the learner has corresponds to the grammar that the oracle has, but that's not natural in a natural language learning setting. So this is very bad. So because what does it mean? Well, like I said, we have this family of languages. I can call it L, but really I want to say we've got a family of natural languages. So L describes the family of natural languages. And we already know that certain properties in these natural languages, like center embedding, like cross-zero dependencies, are really not part of the class of regular languages. So we already showed in my previous slide, I showed that the family of regular languages is not learnable in this learning setting, but we know that we're learning these natural languages. So something is seriously wrong, and clearly it's not the mathematics. So something else is wrong. So either the family of natural languages is in the family, or is in something smaller than the family of regular languages, or the learning setting is not correct, or the language family is something completely different. So there are several other options what's going on. If we kind of translate that to the natural language, the natural sort of linguistics, the field of linguistics, we see that there are different approaches to how people learn language, or the different ways of what people think how people learn language. So there's the nativist approach, where the idea is that people have an innate ability to learn the language. And that means that essentially the language family that needs to be learned is already kind of innate knowledge. You're born with this. And you also have the empiricist approach, which says, no, language is nothing special. It relies on how we learn. So the fact that we learn how to grab something, or that we recognize that things are objects by looking at them, these are also learning capabilities, right? Learning properties. So language learning depends just on our learning capacity, which is more general. So the learnability of these natural languages depends on different things, right? The class of languages that contain these natural languages, but we also need to have a proper representation of the learning process. Okay, so that was the formal approach. Now, the formal approach, I've shown that there are a few issues there, right? We need to, this is clearly not resolved at all. We need to rethink either the description of the learning process or a description of the family of languages that we want to tackle. So what we also can do is, just forget about that formal approach for now. Why don't we just try it? Why don't we just build an algorithm and see if we can get it to work, can get it to learn natural language, and then just investigate what's going on in this algorithm. So we can just take anything, genetic algorithms or neural networks are quite popular at this point in time. Why don't we just take these, teach it how natural language works, and then dive in and see, what was now really going on in there. Of course, you can also take algorithms based on mathematical principles like Occam's razor, Kolmogorov complexity, or minimum description length, for example. That's kind of forcing us to think about, how should we learn? So this is typically called the empirical grammatical inference. Now, there is a slightly alternative point of view regarding empirical grammatical inference, where the focus is very much on what's happening in nature. So what do humans do? So you can actually look at properties of mistakes that children make during language learning, and you want to have algorithms that kind of mimic these mistakes. So if we can find algorithms that actually, while learning, make the same mistakes as humans, that might actually give us a clue about what representations we have in our head. So that's an alternative way of looking at this. Okay, so the idea of empirical grammatical inference is to define, to identify a particular language given samples, right? So for example, sentences, then we're looking at syntax, so natural language syntax, or we give it words and then we look at morphology, which is the structure of words. And of course, you have to keep in mind now the underlying language family is really unknown, right? We already saw in the formal approach that we don't really know what it is, but now we really have no idea. So if we want to build something, we do need to make a choice, right? So that's kind of driving the family of languages that we can learn. But we can also say, if identification, like exact identification, is impossible, why don't we just provide an approximation, for example? So in this case, the evaluation will need to be different as well. We cannot directly compare the grammars. So the evaluation takes a different approach as well. Okay, so if we want to do that, we need to think about the algorithms. So what parameters are we going to learn? And here, there are a lot of possibilities. So we want to at least learn some sort of structure, right? And these can be very flexible. You might want to think about probabilities as well. But we can also say, why don't we restrict that structure? So we can, for example, take a tree bank, which is a collection of natural language sentences, for example, with structure. We can take the structure from these tree banks. This is what linguists have provided us. But then we still need to identify the probabilities belong to this. Or we can even make it more strict, where we say, we fully restrict the structure. We could take, for example, n-grams, so n symbols, n words in a row. We fix that structure, and the goal is to find the right probabilities. So there are a lot of possibilities between fixed and very flexible. This is really a sliding scale. So if we're learning structure, where we don't set a structure beforehand, we start from a collection of sequences, so sentences, for example, and then there are algorithms that might identify these grammar rules. There's a list of example systems that can do this, RPNI, ABL, or EMIL. And once you've learned these structures, these grammar rules, you might also add some probabilities on these grammar rules. So this is a very flexible approach. Like I said, you can also extract the structure from a tree bank. So these are sentences or sequences with structure, with bracketing structure, for example, that might be identified or assigned by linguists. So there's some linguistic idea or linguistic properties behind these. And if you extract these grammar rules from the structure, your structure is already at least partially fixed. So there's some work in the kind of early mid-90s and 90s that takes this approach. So you start with a structure, but then the idea is that you still need to find the right probabilities belonging to these grammar rules. Or you could say, we completely fix the structure. And this is actually very, how do you say it, effective way of creating language models that are currently being used. So the idea is a little bit like this. You can guess the next word by just looking at a few words of context. So if I say we learned a valuable, then, and what is then the next word? It's very likely that you'll say something like lesson. Yeah, you won't say the, because that simply doesn't fit, or soup or something that doesn't fit that context. So we can say, you know, we only look at a few words in a row. So if we take a bigram, so two words together, we look at probabilities of we and learned and a and valuable, and then we can look at the most likely word following valuable, right? And we can get these counts from example sentences. So this is really just assigning the probabilities to these n-grams. And if you take a larger context, you might be a bit more precise in a way, but you need more data to train. Okay, so quickly to summarize, we looked at formal grammatical inference. This is really a field of mathematics that kind of proves the learnability or unlearnability of interesting language families. So there we looked at, you know, first formally describing the family of languages. We need to formally describe the learning process, and then we try to write a mathematical proof for this. Or we can take this empirical approach that I just talked about, where we say, you know, let's take real language data because we know what it looks like, because we have sentences in English, for example, and we try to build a system that can actually learn from this, and then kind of assign for new sentences, check whether it's part of the language, yes or no. So this is this empirical grammatical inference with the idea that if we can find a system that can learn from natural language data, we can look at the properties of these systems and then perhaps move that over to the formal grammatical inference. Okay, so that's all really nice, but we can, and this provides kind of fundamental results, right? But we can also say, you know what, I don't actually really care. I simply want to have a very engineering approach. So can we just use these in practical situations? And this field is called applied grammatical inference. The idea is not to find an algorithm that, you know, is necessarily learning a particular family of languages in a learning setting, or can try to learn from real natural language data. I just want it to be effective. I want it to do something better than if I didn't have that system. Okay, so now there are actually quite a few areas where this is being used. So automatic speech recognition, machine translation. Actually, this ChatGPT is actually doing something like this, right? So it's seen a lot of example sentences. It's learned some sort of structure from this. And based on that, it can actually either generate new sentences, or it can actually try to recognize sentences. Is this a sentence that's part of English or some other language as well? And I'm mentioning this because I've been talking mostly about natural language, but these systems have also been used in other areas, so bioinformatics, for example, or computer network protocols to do system checking. You can also apply to emotion recognition. So there are certain properties of what humans do to see if we can identify the emotions. I've actually also applied it to music. So can we find structure in music? So there's a whole area, there are whole areas where these can just be used. So the idea is that we want to find structure in sequential information. Okay, so just to wrap up, what I've talked about is essentially kind of three fields, and the last one was just very short. I've talked a little bit about formal grammatical inference. That is a field of mathematics that kind of proves whether a certain language family is learnable in a particular learning context. I've talked about empirical grammatical inference, where we kind of push away for now the formal part. We simply want to see if we can build an algorithm that can learn these languages, with the idea that once we have such an algorithm, we can actually look at the formal properties of these. And I briefly talked about just forgetting about that as well, and just applying these systems in real world applications. And I gave a few example fields where that is actually being done. Okay, now the idea is, the question or the challenge really is, we can take simple approaches, right? We can take these n-grams, they're called k-testable languages in the formal context, and we know that they're a subset, so even a subfamily of the family of the regular languages. So they're even more restricted than the family of regular languages that we know is not powerful enough for natural language description. But what happens if we just use them in an applied context, in a real world situation? And what happens if we can find a more powerful algorithm? So powerful in the sense that it can learn a larger family of languages or a different family of languages. Will this actually lead to better results? And I think it's quite interesting. So I didn't really add a lot of information on this because I don't know exactly what's going on in systems like ChatGPT, because of course a little bit is known, but part of it is also kind of company secrets. But what happens if we replace these with more powerful representations? And can we show this? How can we show this? How can we evaluate these? Okay, so that was really my my presentation. I hope I did talk about describing language. I tried to describe language really from a language learning perspective, and I tried showing that in different contexts. So from a formal perspective, from an empirical perspective, let's just try this, and hopefully I show that these can also be used in practical applications. Thank you.
Yeah, Menno, thank you very much for a very, very interesting talk. Thank you very much.